audible. So I would be starting the introduction now. So good afternoon, everybody. So most of you are from the engineering background. I guess there are about 160 students. Most of you are from the second semester, and also some of you are from the fourth semester. There are also a few students who are from the physics background, my former students who have been doing BSc and MSc. So I welcome all of you to the first introductory lecture on quantum mechanics and quantum computations. There are also a few of them who are my colleagues who are interested to listen to what I have to say, so I also welcome them. At the very outset, let me thank NMAMIT, my institution where I work, for giving this opportunity for me to deliver this course, an introductory course on quantum mechanics and quantum optics. Probably all of you are aware of this word, which is quantum mechanics. A lot of fascination is associated with this word, and also probably quantum computations is catching up in a big way in the recent times. So I'm aware that all of you are probably pretty excited to learn and explore this field, which is indeed very fascinating. But to begin with, let me tell you a few things about what this word really means. So let's try to demystify them to some extent and see what we can learn in this particular course as well. So quantum mechanics is a subject which is fairly theoretical in some sense, but at the same time, most of us do not realize that it's a very experimental subject in the sense that this has been one of those theories which has been put into use in applications in electronics, in chemistry, nuclear physics, in material processing, in cryptography, and in very recently people are trying to build systems that can carry out quantum computations, and these things have been shown promise. So a very vast field of applications have opened up because of quantum mechanics. So it can be studied in two different ways. One can study this merely as a subject which can give you an understanding of how the universe works, which is primarily a physicist's point of view from a theoretical perspective. But you can also look at it from a point of view of an application. So in this particular course, I'm looking at it specifically from a perspective to see whether we can make use of the understanding in quantum mechanics to apply that to computation. So I will mention a few aspects about computations shortly. But in the first part, let's try to understand what do we mean by quantum mechanics. Let's say you take a small chalk and you drop it. What will happen? It will just reach the ground, it will fall down. Now people started asking questions as to why does it fall down? Why does it go up? Okay, all of you know the answers to these questions. Now, starting from the motion of a chalk powder or chalk piece up to the motion of Earth around the sun, or even the motion of planets around the sun, everything is essentially governed by some very simple equations. Most of them are formulated by a great scientist called Isaac Newton about 400 years ago. Now these equations are so simple but so elegant that almost every motion, okay, it's said that almost anything, every motion can always be represented by a set of equations called equations of motion. And these equations of motion are essentially cast into that particular form by the simplest laws, such as Newton's second law. So the entire working of this universe, most of the things that you see around you, starting from a dust particle to large planetary systems, follow these simple laws. And this in general, as a collection of all this phenomena, is studied under what is known as classical mechanics. So if we are able to study everything through classical mechanics, then why do we need another set of uh, laws, or why do we need another set of equations or a branch at all? So this is a question that comes to your mind. Around the turn of the 19th century, the beginning of the 20th century, people started realizing that there are certain phenomena like the black body radiation, the photoelectric effect, and Compton effect. These could not be explained with these simple laws of classical mechanics. So they started wondering why this is so. And in fact, unlike other subjects like relativity and different branches of physics or electrodynamics, relativity was mostly put forward by Albert Einstein, and electrodynamics, we owe most of its formalism to uh, Maxwell. Quantum mechanics is not developed by a single person. It was developed by the combined effort of close to about 20, 25 people, most important people, starting from Niels Bohr to Richard Feynman, who gave a fairly new formalism for quantum mechanics called the path integral formalism. And all this happened in a span of a very small span of 20 to 30 years, 1900 to 1930. Almost all the quantum mechanics that we know, which forms the basis of chemistry, of materials, understanding of the materials, or even nuclear physics, and so on, it was all formulated in a very short period of time, over a period of about 20 years or so. This is what makes it very, very fascinating. Now, people often ask this question as to whether quantum mechanics is difficult to study. I should tell you that it is not difficult at all. Quantum mechanics, interestingly, contrary to many people's belief, has a structure which is much simple to understand in terms of the underlying mathematics compared to classical physics. Classical physics indeed is quite intricate and makes use of elaborate mathematical formalisms, but the quantum mechanics, on the contrary, has a very simple structure. But then why is that it is difficult to understand? So I was listening to one series of lectures given by Professor Shankar, who has written some wonderful books in quantum mechanics. So he says that if there is anybody who has understood quantum mechanics, then there is something wrong with the person. So why this particular notion exists among people that quantum mechanics is difficult is because of a particular reason, which is common to both uh, subjects like relativity and quantum mechanics. The reason is simple. Normally, what we have is a notion of common sense or intuition. And our notion of intuition or our notion of common sense is usually applicable to the phenomena around you. So, what do you mean by common sense? For example, if you take uh, an object and if you push the object a little, it will move a little. If you push the object a lot, it will move more, it will move further. So, this is common sense. So, this is also called a method of induction, inducing method of logical induction. But unfortunately, in quantum mechanics, this method doesn't work. So which means if you are trying to extend your common sense, and if you say that, okay, in this particular phenomena, this was what was observed, so I would therefore conclude or intuitively guess that in this phenomena, which is related to this, it should be something like that. So this intuition miserably fails in most of the cases in quantum mechanics, which I will illustrate through a few examples. Now, if something doesn't work to your common sense, what we normally say is nonsense, right? This is nonsense. But basically, it is not really nonsense, but it is a different kind of sense. So, in science, any particular method or any particular branch of knowledge need not always make sense to your intuition, but it should have a sense of logical continuity when it is defined through a set of mathematical rules. There has to be a mathematical framework which can explain this. So what happened from 1900 to 1920 is that scientists were able to develop a mathematical formalism. They did not completely develop the mathematics. Mathematics was already there, but they used a particular mathematical tool to develop a framework of mathematics which could explain quantum mechanics. And that is the reason why quantum mechanics is so fascinating. But at the same time, it is possible to logically understand how quantum mechanics works if you understanding the underlying mathematics. Therefore, you can definitely expect that this course will have a lot of mathematics involved in it, but it will be fairly simple. So I would like to tell you that the prerequisite of this course is essentially basic calculus. So you don't need anything more than that. I would be touching upon matrices. So it would be nice if you can know the basic operations in mathematics. It's not necessary, but it will be helpful. I will actually go into the details or the basic ideas of all this in the course itself. I will start from the scratch, so you don't have to um, worry about the fact that you probably do not know much of mathematics. But I would expect that you know basic differentiation and integration, which we are going to use to some extent in the quantum mechanics course. So there are a couple of things. Okay, now let's come to the computations part. So why we are talking about computations? You know that in a classical computer, again, I'm using the word classical computer because we are envisaging the possibility of what a quantum computer is. So if you look at the computer, the processor of the computer, it's essentially made of a large number of transistors. So ever since the advent of the technology, the invention of transistors, there hasn't been any major change in the the original technology, the basic technology that is underlying all computational aspects, which is essentially a transistor, which is a switching device, and one is able to develop what are called logic gates by using flip flops, and one can have memory by uh, having the states zeros and ones, because essentially when you switch, you can switch a state 0 to state 1, and you can then think about storing them as memory in terms of 0 and 1s. For example, you have your name, and my name is Satyajit, so S means 000010, and so you can code it like that, and everything that you have can be stored in terms of zeros and ones. Also, when you do a computation, essentially you go through what is called um, logical operation like AND gate, OR gate, and so on. And all this at the level of hardware is actually handled by a switching circuit, which is transistor. Now, once the quantum mechanics was developed, people found there is a possibility that these basic operations that we are talking about will have a totally different logic if these states are not states of 0 and 1 in a classical sense, but if they are zeros and ones in the quantum sense. So you might be wondering because you do not know what I'm talking about, but all you need to right now understand is that instead of 0 and 1, the bit representation, in quantum mechanics, there is an analogous representation of what is called a qubit. So we will be studying what a qubit is and what kind of an operation one can do on that, and what is the underlying quantum mechanical property that makes it so different from a classical logic, and what are the possibilities involved. So since I'm yet to elaborate on the various interesting aspects of quantum mechanics, I will not be able to tell that in detail. But what I can tell you is there are a few fields, for example, in encryption, where you need to lock a particular system with a very intricate lock. You can think of a 300-digit prime number to be factorized is a very phenomenal task that can be used for encryption. there are certain aspects of quantum mechanics which helps us do this encryption make much more robust, sometimes uh, extending to a possibility that a single lock can be what can be broken in a day, or what cannot be broken in let's say 60 years can be broken in 1 year using quantum description and encryption. But if you turn it around and say that if you have a lock which is built through a quantum encryption methods, can't be even opened even if you try to do it through combinations for several years, like 50 to 60 years, which makes it as an ideal candidate for encrypting highly secure data. So there are many fields in the broader umbrella of quantum computers, like data, security, and storage, and so on, where quantum mechanical aspects might play a significantly new role in giving a totally different kind of a system, bringing in what people call as a paradigm shift in the entire understanding of how security works, and so on. So we will be talking about very basic operations of logic gates and so on after the quantum mechanics lessons are over, and then I will use what quantum mechanics we learned to show that these can also be done with analogous quantum operations called qubits, using qubits, and how it fundamentally differs. So I will give you an overview of how one can apply quantum mechanics to the field of quantum mechanics, quantum computation. But you should remember that this is a very short period of time, so we need to make a balance between studying quantum mechanics and also trying to apply it to a certain field, in this particular case, quantum computations. So the this, the line of action would be that we are not going to go too much deep into the theoretical aspects of quantum mechanics, because we are eventually going to make use of the concept to apply and try to do certain simple problems to understand how quantum computations come about. But at the same time, it is not uh, easy to do this unless you have a reasonably good grip of quantum mechanics. So therefore, I will not also be doing it very lightly. The course will be quite rigorous. So I expect that you put in some effort. This will be fairly mathematical. But again, as I told you, I'm not going to intimidate you. This will be simple mathematics. But where is the difficulty coming from? I have already told you the difficulty comes from conceptual continuity. You will understand the mathematics, you will understand the logic, but how it fits together to give you a physical reality. So this is where the difficulty might come in. So that is where I'm trying to help you. So with this in mind, a word of caution about references. I will not give you, it will not be possible for me to give you a single reference book, mainly because the continuity of the thought that I have, that I present you, will not be the same as the book. So if you read the book, there is a possibility that you will be able to see the mathematical structure there. For example, suppose I'm doing some matrix addition or diagonalization or something like that. So the book will also talk about what is diagonalization and what is matrix addition and so on. In that sense, you can actually use the book, but the approach or the thought process will be slightly different. So what I will do is, as and when I take the classes, I will tell you the corresponding portions that you need to refer to, and most probably I will give you the soft copies of those portions in the PDF form so that you can go through them. But how these different portions connect? So what exactly is the thought process and how does it evolve? So this is something that you need to keep in touch with the lectures, and I will possibly give you an outline of the lectures, something called a lecture notes, not a very elaborate lecture notes, but the mind map of where we start and how we go about it. So this will help you to keep the thought process continuous, and each one of these parts will have segments. For example, there might be a topic on operators, there might be a topic on matrices, so you can go to the relevant books for the sake of practice to gain more insight into understanding this. But I can mention one book at the outset, which is Quantum Mechanics by Griffiths. So you can read this book. It's a very nice book, and that should really help you. But I will not be sure whether the way in which he takes the journey will be similar to what I do. So you can't really take my lecture and compare and see what it's saying. But if you're interested in reading and trying to make an attempt to understand quantum mechanics, that's a book that you can use. I will also send a list of other references that I'll be using so that you can go through them also. But I suggest that you mostly focus on my lecture because reading multiple books sometimes might make you a little confused. Okay, so at least for the first 10 to 12 lectures, you listen to the lectures, and after that, you would be probably in a better place to be mature enough to go and read those books to find out what would be the best book for you. So this is essentially what I had to tell you about quantum mechanics and also about the application of quantum mechanics in the field of quantum computations as a very brief introduction. So next class onwards, I would be starting with the concept of an atom, because it is essential that we are employing atoms to do the computation. Okay, so if you are employing somebody, you should know about that person very well. So far we were employing transistors to do the calculations, and the switching of the transistor, the state of the transistor is what was doing the trick there. And in this particular case, in quantum computations, we are going to employ individual atoms, the state of the atom. Okay, so what is the state? We will discuss that in detail in the coming classes. But the state, a certain state that belongs to a property of the atom, is what is being used in quantum computation. We are actually employing atoms to do the computation. They will do the computation for us. So it is therefore necessary to understand how they behave, what is their nature. So they do behave very differently than bottles and pens or chalks or planets. Okay, if they were to behave similar to planets, or if I throw a chalk, or if I fire a bullet, how would the bullet move? About the trajectory of the bullet. It will go in a parabolic path. So if I shoot an atom, okay, so how will it move? Now this is going to be fairly different than anything that you have ever seen. Now this entire world of subatomic particles will not behave in the sense they misbehave, you can say, from the point of view of classical mechanics. But they actually don't misbehave. They have their own set of rules, and those set of rules are essentially what forms quantum mechanics. And we are going to learn the laws, the principles of quantum mechanics, and the underlying mathematics which governs those principles. So this is essentially what I'm going to do. So if there is anyone who is attending this particular course just for understanding and not going through the grading part, they can probably take leave. I will be discussing about certain aspects of how do we grade this course and how do we manage this course. Most of you are from NMAMIT, so you will be on the Moodle. So I will be handling these things on the Moodle. But rest of you, there are a few other students who are also in the audience. I will be conducting some tests for them as well. So I will give you a very brief description of how this is being done. If anyone else is also willing to take the quiz and the test, they are also welcome to do so. The number of students is very large, so you can already imagine that I will not be able to do any descriptive kind of tests, but there will be certain very carefully planned examinations which are multiple choice, but those multiple choice questions won't be very simple, in the sense that will test your analytical understanding and that will also test your numerical understanding. For example, let's say I ask a question, numerical question, which says what would be the energy needed for an atom to go from a ground state to a higher energy level. Then you have to actually do the calculations, and the numerical answers would be close to each other, so you won't be able to guess them. So you have to actually do the calculation, but you have a choice, multiple choice from which you can choose from. So it will be a little rigorous, the quizzes. I probably conduct something like 4 to 5 quizzes over the period of this particular course. And these quizzes are being done for you to actually, assess your level of understanding. So basically, what I'm going to do is there could be also a couple of assignments, and again, the assignments are also um, graded digitally, which means I will either be having 5 marks or 10 marks, and no in between marks, or if I have a 20 marks assignment, there'll be 5, 10, 15, and 20. But these will have what is called a rubric, which means I will give you the meaning of these marks. For example, suppose I ask you a question. If you are able to understand the question, you will get 5 marks. Okay? If you are able to understand and attempt the question, you get 10 marks. If you are able to do something and solve the problem, you will get 15 marks. And if you do extremely well and give extra examples and so on, you get 20 marks. So the idea is that you will know where you stand. Okay, so you know how far have you understood the subject. So this is an indication of where you are. Okay? So don't take this as a threat. Don't let the fear of examination bother you, but rather it will give you an assessment of your understanding of the subject. So based on that, you can approach the subject or the learning methods to see where the improvement is actually needed. So that is about the assessment. But this is not very important, as you already know. This is not going to count on your overall academic performance, but this is a value-added course for most of the students from NMAMIT. So you have to give it some seriousness, especially if you want to understand the subject, so that it can reflect in a good certification. But if you feel that you don't need to get the certificate and just want to learn it for the sake of learning, and if you feel the process of grading will come in the way of your enjoying the subject, then please feel free to not write the quizzes or not opt for the certificate at all. So I would even then suggest that probably you can give up your ideas on certification, but you can still write the quizzes so that you will know where you stand. But I encourage all of you to write the exams so that it will give you a better feedback in your understanding. Okay, so I don't see somehow any text happening. I don't know, there is some thing has been disabled. I'm not able to see the chat communication. So what we can do is we can take these questions on the Clubhouse. So I will activate the Clubhouse and I will close the video. And then if you have any questions, we can take this question in the last 10 minutes. So we'll have 10 minutes of discussions. I would be happy to answer your questions on anything based on learning process. And I would be happy if the questions are more on quantum mechanics and less on, sir, what about attendance and things like that. Of course, we will send you the details of what is necessary in the group. So we will be, just a second. So we will be sending you the details, so you can be available. Suresh will help you in this particular aspect. So now I'll mute my. You probably are able to hear me on the Clubhouse as well. If you're having the Clubhouse app and if you're able to listen to me, or if you have not joined, you can go ahead and join. And if anybody wants to ask questions, you can raise your hand and we will pull you up one by one. We will have the discussions. So I will stop the stream right now and we will have the discussion on the Clubhouse.